In this relatively short lecture, we will discuss how to use theoretical distributions to describe random values. This approach is also called parametric approach, and the first thing I would like to discuss is what is actually parametric approach and how do we use parametric approach both in science and in statistics. So let's start with parametric approach in science. Okay. I will show you two examples, one from physics and one from biology. Just some very simple examples so that you understand how parametric approach works and what are benefits of using parametric approach. Let's say we have a piece of metal, okay? We don't know what metal is it. And we would like to investigate how this metal conducts the electricity. What can we do? We can use some wires to connect a battery with some voltage, for example, 1 volt or 2 volts and so on. Then measure the current in the circuit. So how much amperes we have in the circuit, okay? Then if we, so I will call it, this is voltage and this is the current. Then if we change the battery, for example, from 1 volt to 2 volts, of course the current will change as well. If we continue changing the voltage and record what current we will have in the circuit for every voltage, we can make a plot. So we have, for example, here we have a voltage, U, for example, 1, 2, 3, 4, 5, 6, and so on volts. And here we have some current and some units like ampere or milliampere, depending on what metal you use. Okay, so here we have a current in amperes, and here we have the voltage in volts. Okay, so if we do these measurements, we can see that actually you will get some points. For example, if we do 7 measurements, you will get some points like this, and like this. So you will see some linear trend. Okay, so it means that the current depends on the voltage linearly. So what you can do in this case, you can make a line fit, something like this. Find a line that fits all these points very well. And you know that the equation for line is the following. It's y equal to ax plus b, okay? Where y is our current, so this is y, and x is our voltage, so this is x, okay? So these two coefficients, a and b, are called parameters of this function, of this linear function. And then you can estimate it. The parameter b, this one, it's where the function crosses y. So it means that if we don't have any voltage in the circuit, what will be the current? Of course, if we don't have any voltage, the current will be 0. So b equal to 0. B equal to 0. And then a is the slope. So if you take this line and find the slope, so it will be the ratio between this and these segments. So a tells you the slope of this line. Okay, for example, if the slope 1, it will correspond to 45 degrees. If slope 0, it means that it's parallel to x. If slope is infinite, it will parallel to y, and so on. So this parameter a is a very important one because it tells you what will be the current if you change voltage by 1 volt. Okay, so how good your metal conducts the electricity. Imagine that you take another piece of metal, okay, and then you repeat the experiment and got something like this. Okay. It will not be ideally lined, but it will be very close to a straight line. Okay. Again, you can make a line fit, something like this. So you can find another parameters. Let me call these parameters A1 and B1, so it's for the first metal. And then we have y equal to A2 x plus B2. Again, B2 will be equal to 0 because it doesn't matter which metal you use. If you don't have any voltage, the current in the system will be also 0. Okay, and A2 will be the slope of this line. So I will just try to make a drawing. So this is the slope. Okay. And then you can see that the slope for the second line is larger than the slope for the first line. So A2 A2 is larger than A1. Okay, what it means? Let's think about that. So if you have, for example, 3 volts, in the first case it will be this voltage, it will be this current, but in the second case, it will be this one. So the current in the second case will be larger. So it means that the second metal conducts the electricity better. So you can think about A as a measure of conductivity of your metal, how good your metal conducts the electricity. And if you take the inverse of A, for example, 1 divided to A, it will be a resistivity or resistance of your metal. Okay, then the same for the A1. So you can see that if this is true, then you can say that, so if this is true, you can say that R1 is larger than R2. Okay, so it means that the resistance for the first metal is larger than the resistance than for the second metal. And then you can use all this intuition to make a Ohm's law. So where you have I equal to U divided to R. So the larger R is, the smaller current is for the given voltage. So this is the Ohm's law. Ohm's law. Okay. So that's how parametric approach works in science. So we do some experiments, we get some experimental data, like 10 or 7 points in this case, and then we use known function that describes our data very well. In this case it's a linear function. Calculate parameter of this function, and then use these parameters to describe the data as well as to compare the data. So in our case we have 2 parameters. One is always 0, one is not 0, and the parameter A describes some property that and parameter A describes the properties that we can identify using the experimental data. So very simple approach. Get the data, feed the data with a known function, calculate parameters of this function, and then use these parameters to describe the data and to compare the data like we compared these 2 metals.